Oh shit. Hey yo, what's up, YouTube? It's your boy Joshhabram. Let's check Moodle. Let's check if I have the assignment. Like I did not look into the chemical kinetics assignment. There should be an assignment. Assignment number 10, exercise 10. Running out of time. Oh, what the hell? Biological systems. That's what we want. Yes. We're getting close. But if you don't mind, let me go to the what's it called? Let me go grab some coffee, okay? Let me go grab some coffee. Cause I need more motivation. I'll be right back, people. Be right back. Where are my headphones at? Whiskey, we big, we big. Oh shit, I forgot about the jacket. Should I keep the jacket or I think it's better to be there. Oh. Okay. So, example 37. ChatGPT, go. Am I hearing something? No. Okay. Most chemical reaction in biological systems was catalyzed by enzymes. A prominent theory describing enzymes kinetics was introduced by Michels. Mi- Mi- oh Lord. Okay. Okay. So, they propose that an enzyme substrate complex forms in pre-equilibrium state from which the product is generated in consecutive reaction steps. They propose that enzyme substrate complex forms in pre-equilibrium state. What? Enzyme substrate complex forms in pre-equilibrium state from which the product is generated in consecutive reaction steps. State the general reaction equation that shows the formation of enzyme substrate complex and its consecutive conversion to the product. Use the following abbreviations: E enzyme, S substrate, P product. Mm-hmm. General reaction equation: Michaelis-Menten mechanism. Michaelis-Menten proposed that the reaction proceeds via trans transient enzyme substrate complex. What? I still. Also. Could. The reaction equation written enzyme plus substrate gives enzyme substrate. The that is the entire Michaelis Menten mechanism. The enzyme appears the enzyme appears again on the product side, meaning it's not consumed. Oh. Mm-hmm. Okay. Enzyme plus substrate gives intermediate enzyme substrate, and this enzyme substrate is slowly converted to enzyme and product. So substrate is what's been converted to product. Mm-hmm. What does pre-equilibrium state actually means? Pre-equilibrium refers only to the step 1. E plus S gives ES. This part reversible reaches at the beginning. ES forms quickly. ES also dissociates back to E plus S. No significant amount of P is formed yet. That's why it's called pre-equilibrium. What consecutive reaction step means after the ES complex exists? The second step follows ES plus ES gives E plus P. This step is lower rate determining responsible for all the product formation. Consecutive simply means one step happens after the previous one. So this sequence is enzyme bind substrate. So these would be second order reaction, right? So this enzyme substrate reactions are second order. $80 subs. I just saw my channel. We got 80 subs, son. That's crazy, dog. That's crazy. I don't know what happened to the. Wait. Wait. Oh. What did you do, OBS? Like, that's weird. Okay, if you don't know what was going on, I was using OBS and OBS just shut down. And that should be showing up on my YouTube. Like it should be showing up like should be showing up like two live streams, right? But I did not. But yeah, just show there's only one live stream going. That means even though OBS crashed, the stream did go on. How? How? That's what happened. I don't know. What's the problem? I get distracted. Why am I getting distracted? Focus. Focus. Short answer, no, not a general. Now, the precise explanation you need for the exams, the elementary binding is second order. Yeah? But ES is not independent. It depends on total enzyme concentration, substrate concentration, equilibrium constant. Parent reaction order does depend on substrate. Why enzyme reactions are special? Normal chemical kinetics. Enzyme kinetics involves a bound intermediate rate is controlled by enzyme saturation, cannot be described by a single integer order. Exam safe conclusion. The formation of enzyme substrate complex is a second order elementary step, but the overall enzyme catalyzed reaction does not have a fixed reaction order and follows Michaels-Menten kinetics, showing that first order behavior at low substrate concentrations and zero order behavior at high substrate concentrations. Okay. So the enzyme that form then the substrate to product. So from this enzyme does not give out anything from it to change the substrate to the product. So how exactly is the enzyme is it just changing structure of the product? Changing the structure of the product or structure of the substrate. Or is it somehow adding the necessary bro, get the fuck out. Bro, ChatGPT is so slow. Come on, pump it up, pump it up. There's one more guy. We got DeepSeek. I'll prepare DeepSeek right now. Let me just make it's example sheet 10. Oh, what did I do? Okay. Short answer, tell it like it is. An enzyme does not get consumed, but it does actively participate. Yeah, I understood that enzyme does not get consumed, but then how I don't get the thought process. Like, does enzyme work in a way that it utilizes the other components to convert the substrate, uh, or does the structure of the enzyme helps in changing the structure of substrate? You know what? I should look up an example. An enzyme does not get consumed, but it does actively participate. It's not just holding the substrate, it temporarily interacts with the substrate, redistributes electron, stabilizes charge, sometimes temporarily transfer atoms or groups, but in the end, everything given is taken back. Uh-huh. Yeah, okay, everything given back is taken. But how enzyme lowers the enzyme changes the pathway, not the overall chemistry. Enzyme lowers activation energy, not delta. It changes the pathway. From what I understood, enzymes make the process faster. What enzyme does mechanistically? Oh, enzyme catalyzes reaction by temporary interactions. There are several mechanisms often combined. Structural distortion, strain. Enzyme binds the substrate and forces it into a strained geometry. Bonds are bent or stretched, transition state like geometry stabilized. This makes the bond breaking forming easier. The enzyme pushes substrate uphill halfway. Acid-base catalyst is very common. Enzyme change side range can temporarily donate. Okay. It acts as acid or base. acts as a proton shuttle. Covalent catalysis. The enzyme forms a temporary covalent bond with the substrate. Okay. Okay, could you give me a common example carbonic anhydrase overall? Example. Why is the example perfect? Only small molecules involved. No atoms are permanently taken from the enzyme. Shows acid-base catalyst and metal ion catalysis essential in blood for CO2 transportation. Okay. What the enzyme actually does: binding and activation of water. Carbonic anhydrase contains zinc plus ions in the active site. Zinc binds with water molecules. Okay, I can't read any of the reaction you show me. It looks like gibberish. Is there any way I tell, or any prompt I can use to get you carbonic anhydrase? The issue is latex chemical notations do not render clearly for search. Plain text chemical equations. Okay, I'll have to remember that. Plain text chemical equation. Okay. Ooh, it's cold. Ain't gonna lie. Carbonic anhydrase reaction CO2 plus H2O gives H2CO3. Oh, this is the slow reaction. Okay. So, can you show me how the carbonic anhydrase enzyme speeds up the process? Oh no. Oh. Uncatalyzed reaction slow in water. Carbon dioxide reacts like this. This reaction is slow on its own because CO2 is not very reactive. Water is a weak nucleophile. Proper orientation is rare. What carbonic anhydrase does, big picture, does not get consumed, does not permanently change, lowers the activation energy, makes the reaction 10 raised to 6 times faster. 10 raised to 6. It does this by providing a better nucleophile holding molecules in correct orientation, stabilizing charges during the reaction. The active site, key idea. Inside the enzyme, there's zinc 2 plus ion. Zinc 2 plus is bound to the enzyme water molecules. Zinc 2 plus makes the bound water molecules more reactive. Step by step mechanism. This is speed up. Water activation crucial. Oh, it's cold. Enzyme. Okay. Carbonic anhydrase. I need the chemical structure or chemical formula. C1285. Mhm. That's a big molecule. Uh-huh. Dude, okay, that's like one CO2 has one carbon, right? And this enzyme has 1285 carbon. That's like let me see the comparison. 1 versus 1000. Can I see the numbers? No, not these. I just want to see. YouTube, Google does not get it. So there's an enzyme 2 plus ion, and zinc is bound to the enzyme. Wait, zinc is bound to. Okay, there you go. That's interesting. I need to know how many CO2 molecules does the carbonic anhydrase act on. Zinc 2 plus makes the bound water more reactive. Step by step mechanism. This is speed up water activation. Enzyme C2 plus H2O. Enzyme 2 plus OH minus. Okay, it makes it alcohol. Water loses H plus easily. Now we have OH minus, a strong nucleophile. Without the enzyme, this step is very unlikely. Ah. CO2 binding and attack. Why this is fast? OH is already positioned correctly. CO2 is held close to the active site. What's the product? Oxygen? I'm gonna be right back. CO2 plus OH minus, it's trio minus. Product releases. Creates a strong nucleophile. So, from what I have understood, the enzyme makes use of the water molecule to create the nucleophile nucleophilic OH minus, and again uses at the end to regain the original structure. Regain. H2O is a requirement. Think. The enzyme is like 1000 times bigger than a CO2 molecule. So how many CO2s? Is it one or many? I'm guessing one, because there is only one zinc atom. Water is required. Enzyme uses water molecules at a time. Water is regenerated at the end. Water is not consumed overall. Mm-hmm. Water. Water plays a big role. So the net reaction remains even though water actively participates inside the active site. How many CO2 molecules bound to an enzyme at once? Answer 1. Reason carbonic anhydrase has one active site. So one CO2 molecule attached to the enzyme is 1,000 times bigger. Thousand times bigger. Hmm. Only one substrate molecules can bind per active site at a time. So the situation is one active site, one zinc 2 plus molecule, one CO2 molecule at a time. Why the enzyme size does not mean multiple substrates bind? That's very important conceptual point. Even though the enzyme is much larger than CO2, only a small pocket is catalytically relevant. The rest of the protein is structural for correct folding, for positioning residues, for stability. Yes, stability does make sense. So big enzymes, not many substrate at once. Active site number determines capacity, not size. Mm-hmm. Okay, even though the enzyme is much larger than CO2, big enzymes, active site number determines capacity, not size. Yes, but sequentially, not simultaneously. Mm-hmm. Carbonic anhydrase enzyme can convert 10 raised to 6 CO2 molecules per second. Per second. Mm-hmm. Ten raised to 6. 10 raised to 6. So it takes about 1 10 raised to minus 6 second per CO2 molecule. So that says how small these things are. Ten raised to 6. So weird. This shit's so weird. Why only one ZN2 plus is enough? It's a catalytic center responsible for activating water, precisely positioned. would disrupt the structure would not increase rate per enzyme molecule. Why? Nature optimizes, not maximizes blindly. 10 raised to minus 6. Raised to minus 6. Wait. So I got this one. Quantitatively sketch an energy profile, free enthalpy versus reaction coordinate for the case of uncatalyzed reaction S to P and case of enzyme catalysis indicate the activation energy for uncatalyzed as well as catalyzed reaction indicate the rate determining steps for both cases. So, dude, too much coffee, I'm vibrating. I'm shaking. Don't don't draw the graph, okay? If you have to make the graph, give me the Python script for it with the name. I'll make the graph in PyCharm. What happened to PyCharm? You stupid, you did not give me a name. There we go. Paste stuff. Okay, no, paste. Get the fuck out of here, bro. So involvement of a bigger molecule resulted in a slower activation energy. I'm just saying this, just not as a chemist. I'm just saying the involvement of a bigger molecule such as enzyme results in change in activation energy. Mhm. Indicate the activation energy for uncatalyzed as well as okay. Indicate the rate determining step for both cases. Huh. Rate determining step is the slowest step for a reaction that effectively controls the overall reaction rate on an energy profile. It corresponds to highest energy point along the reaction coordinates. On catalyzed reaction, the substrate goes directly to the product. There is only one molar major step, so the RDS, a single transition state at the top of energy barrier. Activation energy is high, meaning the reaction is slow without a catalyst. Enzyme catalyzed reaction, enzyme catalyzes the substrate and or the transition state, effectively lowering the activation energy. There are multiple steps: substrate binding, formation of enzyme substrate complex, chemical conversion, product release, but usually the slowest step among these is still the RDS, rate determining step. In many enzyme catalyzed reactions, the chemical transformation with the enzyme substrate complex is RDS. On the energy profile, this is shown as lower peak compared to uncatalyzed reaction, but still the highest point of the catalyzed path. Summary for your sketch: uncatalyzed single high peak RDS at the top, catalyzed lower peak RDS at the top of the catalyzed curve. RDS shows where the reaction bottleneck occurs and the enzyme works by lowering this barrier, speeding up the reaction. Mm-hmm. I still didn't. Again, I didn't get the RDS for the catalyzed. Are the RDS same for both, or is there a common RDS here? RDS is conceptually the same for both, but in practice, the activation energy and get the hell exact location along the reaction coordinate differ. Uncatalyzed reaction, there is only one step, so the single transition state is RDS. Okay. Oh, indicate the activation energy for uncatalyzed as well as catalyzed. Indicate the rate determining steps for both cases. Mm-hmm. Is enzyme catalysis to be categorized as part of the homogeneous or heterogeneous catalysis? It would be heterogeneous, just from the wording. I don't know. Homo. Okay. Homogeneous catalysis, the catalyst and reactants are in same phase. What do you mean phase? For most enzymes, the enzyme, catalyst, and substrate are both in aqueous solution. Same phase, okay. The enzyme forms a transient complex with the substrate in solution, accelerates the reaction, and it's regenerated. Okay, so could you explain more on the term homogeneous? Because if it's just whether if the but if we consider homogeneous mixture, is this does this one have to the mixture uh, homogeneous catalysis and reactants are in different phase. The focus is still on the phase difference, not the uh-huh. Mm-hmm. Given quantitative sketches showing how the concentration of substrate, enzyme, and product vary over time. There's no add button. Fucking idiot. Stupid. Stupid. Mm-hmm. Enzyme substrate complex concentration. Product, okay. And substance. Free enzyme. Well, it's like, okay. It's five. Yeah. I guess I gotta cook something. I gotta call my parents. Sure, let's go. Free enzyme. This represents the enzyme that is not bound to the substrate. At the start, most enzyme is free, so E is high. Now, free enzyme is just same as substrate. Wait, intermediate complex where a substrate is bound to the enzyme. Initially, a substrate and enzyme meet. ES rises, reaching a maximum when substrate binding is at its peak. After that, the substrate gets converted to product. ES decreases because the bound substrate is now turning into product and releasing the enzyme. The curve typically looks bell-shaped, peaking somewhere in the middle of the reaction. Okay. Hmm. Okay, you know what? I gotta cook something. We'll continue later. Peace out, YouTube.